So now that we're getting into the math, let me hit record. So yeah, this is one of these parameterized surfaces. Again, not too horrible of an equation, all things considered, but if you were to try to transform this into Cartesian, x's, y's, and z's, it would just be a monster. And so, okay, that's why parametric surfaces are kind of a worthwhile thing. They are a necessary evil, I suppose. Let me go ahead, while I switch over to my iPad here, I will answer a few questions. Is this lecture being recorded? I wish I would have taken that question a little bit earlier. Thank you. Thank you. Thank you. What is above the R UV? So that's just a little vector symbol. So this is just saying that it has components. So it has an X component, a Y component, and a Z component. It is a vector function. Oh, you guys are, they have you trained so well. Is this lecture being recorded? You are, yeah. It's good that you're looking out for the other students. Why do we use 2 parameters and not 3? That's a fun one. Because, like I talked about a little bit here, is that these are 2-dimensional items. We're not talking about, like we talk about maybe a very easy surface. We'll talk about a sphere, right? I'm just talking about the surface of the sphere, right? And if you were to build the sphere, right, you would need to build it out of paper, right? The surface itself you would build out of paper. I'm not talking about the sphere and its insides. If you have the sphere and the insides, then that is a 3-dimensional region. And yes, you would need 3 variables for this. But because it's just a 2-dimensional region, a 2-dimensional surface, that's why you only need 2 variables for this. All right, let me make sure that I'm not, let's see. Okay, good. Let's see, let me hit this. Okay, so with this, why don't we go ahead and do one of these kind of problems that you could see on web work, on a quiz or an exam or things like this. So identify and sketch the surface. So here we're given a parameterization and we want to know what on earth it is, right? And so we can see that we have some things with u's and we have a v kind of by itself, right? And of course this v is independent from u. You can see that it doesn't really rely on u or anything like this. And so I'm thinking that already that, this is the y coordinate right here. Maybe this surface here doesn't really rely on the y variable. Now, of course, right, with all of these u's hanging around here, I can find out an equation to, bring together these x's and z's. Let me just go ahead and label these just so everyone remembers. And of course, the most famous equation that kind of ties together sine and cosine has to be cosine squared of theta plus sine squared theta is equal to 1. And of course, this is true for any theta value. And in particular, our variable here happens to be u. So we can use cosine squared u plus sine squared u is equal to 1. And now remember, x is cosine, z is sine. So this is really saying x squared plus z squared is equal to 1. And now this other thing, right, y is just equal to v. It doesn't really depend on this at all. So what we're going to have here is this circle. And in fact, down here, if you've already downloaded these notes from online, you probably see this. Right, you have the circle in the xz plane, right? So I just draw it really quick in the xz plane. So here's x and here's z. It's a circle of radius 1. And then, right, y has really nothing to do with this, right? Y doesn't have any u's. It's not tied to these equations, right? U and v are independent from one another. And so y can just be whatever it wants. Y can be 1 or 5 or 100 or anything like that, right? And so this is just going to be, well, if I include in a y-axis, kind of like we have here, a y-axis, it's just copies of the circle, right? Whether it be at y equals 0 or y equals 1 or y equals 2. And likewise, whenever I say y, I could be saying v. V equals 0, v equals 1, v equals 2, right? Because here, y and v are the same. So this is a sketch of what it looks like. And if I wanted to say in words, right, this is going to be a cylinder. And there's no restrictions on my variables. So this is really an infinite cylinder, right? It goes on forever. All right, I'll peek at the Q&A and just kind of see what if there are any questions. Is there any way to make your screen share bigger and yourself a little smaller? That is independent of me, I believe. So if I go ahead, did I get bigger for you guys? I don't know. I was under the influence that, or under the impression that this is something specific for each person. So I think that mine only controls the what's being recorded right now. So me doing that is just influencing my recording. But yes, okay, great. So I do hear that you can change it yourselves. Just drag the picture on the right-hand side, I suppose. All right, awesome. With that, a little bit of side note here. Of course, you can always decide to restrict these variables a little bit, right? You can choose a domain for these variables, for these parameters. So if we have these UV values, and for instance, in this last example that we just did, if I specified that U is ranging from 0 to pi over 2, and V is ranging from 0 to 2, well, then we don't get the entire thing, right? Because again, V is the same thing as Y. So the Y's aren't going to go on forever anymore. The Y's are only going to range from Y equals 0 to Y equals 2. That's going to be the maximum. And if we plug in those theta values into our specific equation, which I think it's worthwhile to do at least one of these, so we'll actually plug in one of these, you'll see that you only get a quarter of the circle, which kind of makes a lot of sense. But the natural question that you have to ask is, well, which quarter, right? How do I know it's in this octant rather than any of the other octants, right? And so we just plug in a few of these values. So if I plug in, for instance, U is equal to 0, and then I'll also do, let's say, V is equal to 0, right? So again, this is just the same thing as Y is equal to 0. Maybe not super exciting here. And again, what I'm plugging this into is this right here. So I'm going to have the point cosine of U. So cosine of 0 is 1. V is 0. And sine of 0. Sine of 0 is 0. So I get 1, 0, 0. So on my picture over here, we go 1 in the x direction, none in the y direction, none in the z direction, right? And so that was perfectly fine and fun and all that sort of stuff. You could also try plugging in maybe U equals pi over 4 and U equals pi over 2. And you'll see that you'll map out this quarter of the circle right here. And that's why it's this quarter rather than in some other octant, right? So you can just plug in a few points to see which octant it lives in. All right, so again, that's kind of if we restrict the domain. I had a request to go and show the picture of the cylinder one more time. So we'll stare at this while I look and see if there were any other questions. If you plug in pi over 4, would you plug in y equals 1? That's an interesting question, and the answer is not necessarily, right? That these things are independent from one another. So you can plug in pi over 4 for U here, and you could plug in really whatever you want for V, right? So V could still be 0 here, and in which case you get this point right here that I've kind of mapped. But if you decided to plug in V equals 1, well, then it would still be at this pi over 4 radians here, kind of. So again, maybe somewhere over here, but now it's been shifted out, you know, by y equals 1 or v equals 1. And if I plugged in v equals 2, right, then it would be all the way here at this boundary over here. So I think one of the questions at the top of the hour was something about, will we be dealing with parameterizing boundary curves? Maybe this was on Piazza, I don't know. It's a blur right now. But the answer is not so much. We're going to be dealing with parameterizing surfaces. But you can see if you're interested in any of these boundary curves, you can just restrict to a specific value for one of your parameters. So for instance, when I restrict to v equals 0, I get this curve right here, which is on the boundary, right? But if I restrict to other v values, I'll get other curves, right? V equals 1 would give me this curve. V equals 2 would give me this curve. All right. With that, I would like to, and this kind of talks just that one of the things that we will be interested in, but we're not right now, is surface areas. This will be an application of double integrals, and so we'll wrap back around to this section later on, but this will not be on the exam. Surface areas will not be on the exam for parameterized surfaces. So if you are reading the textbook, that will not be on there. This is one of these that I would like to skip for the time being, just to make sure that we get to this last problem. This is parameterize the plane that passes through a specific point, given a couple vectors that it wants to contain. But this is in its heart, right? We could do this from 12.5. We really don't need the material from today's class in order to be able to solve this problem. So if there's time, I will come back to it, and you'll see the solutions already. Right, so that's one of the things that Lev gave me, were the kind of the filled-in version of this. So he has an idea for the solutions for this, but I'm not going to give it really any airtime in class because I want to make sure that we can get to some of this other stuff. All right, here's one that I would like to spend a little bit of time with. Right, we want to parameterize this sphere. So the sphere is x squared plus y squared plus z squared equals r squared, kind of a classic equation for a sphere. Maybe the first time through this, let me just pretend, right? Anytime maybe I'm first getting introduced to something like this, I like to have something a little bit more concrete. I mean, this will be wonderful once we have this at the end here, but maybe the first time through, let me say that I'm going to choose a very specific radius. In fact, well, 2 is used a lot of places. Let's not use 2. Let's use 5. Oh, but my 5, yeah, let's use 5. So this would be the same thing as x squared plus y squared plus z squared equals 25. We'll solve this problem, and then we'll use the solution for that problem to help us upgrade and say, how would we do this for any old radius, right? Any r value we'll be able to do this for. So the idea behind these ones, when you're trying to parameterize a sphere, or you'll see here later on, and this will be one that we're skipping, a cylinder, kind of you want to use the coordinate system that is most natural for the object. Okay, what do I mean by that? Well, we just came from a section called cylindrical coordinates and spherical coordinates, right? And so the idea is that we shouldn't forget about this. We should use those as much as possible in order to help us with our parameterizations. And so, of course, if you're given a sphere, I hope your mind will go to spherical coordinates, that if we use spherical coordinates, that we can come up with a good parameterization for this. So let me go ahead and kind of just start with spherical coordinates here. From our spherical section, we learned some ways to transform between Cartesian and spherical. For instance, r, and usually I do a quick pit stop into cylindrical. So I'm going to write down x equals r cosine theta. This is just how I happen to remember it. So I'm here in cylindrical coordinates first, but of course in spherical you don't have r's, right? You have rows. And so I'm going to go ahead and instead of r here, I remember that r in spherical is rho sine phi. So that's the same thing as r from cylindrical. And so likewise for y, I would probably first write down r sine theta. I can remember that all right. And I can remember that r is rho sine phi. And so this is going to be rho sine phi sine theta. And then finally, z is this rho cosine phi. And really what these all come from, and what I did in my pre-class video, I'm not going to get into it right now, but I definitely recommend that you watch my pre-class videos. They're posted on D2L on the same page where you go for these videos if you happen to miss class, right? Is that in this triangle here, we have, this is our phi variable, this is our z height, this is our r, our 2-dimensional radius to this point, and this is rho, our 3-dimensional radius to this point. And using this triangle right here, you can get exactly this, that r is rho sine phi, and that z is rho cosine phi. And so that's why, I mean, I was just thinking about this triangle when I wrote those down. That's how I was able to get it fairly fast. And it didn't feel like, I wasn't really memorizing the equation. It's because, of this triangle right here. And again, just kind of phi being this positive, this rotation from the positive z-axis. Okay. With this, let me finish this problem, and I see that there's a few questions popping up and whatnot, and then I'll answer those. So now that we have this, we're going to use spherical again for this. But the thing is, right, we're not on any old, right, we're not any old point. We're not anywhere in space. We're on a very specific sphere, right? And on this sphere, we have that rho squared is equal to 25. Or another way to write that is rho is equal to 5, right? This is the sphere of radius 5, right? The sphere, that all of the points that are distance 5 away from the origin. And so that's how we're going to kind of reconcile this fact that, right, here we have 3 variables, but when we parameterize something, we're only allowed to have 2 variables, right? And so we need to get rid of one of these variables, essentially. And so the variable that I'm going to get rid of is rho, and it's because we know that rho is always equal to 5 when you're on the surface of this sphere. So I'm going to go ahead and write down x is equal to 5 sine phi cosine theta, y is equal to 5 sine phi sine theta, and z is equal to rho, so sorry, not rho, 5 cosine phi. And so if I wanted to write down a parameterization, and let's say in WebWork you got this question, but it says, hey, I want R of UV, right? So this is specifying that it doesn't want your variables to be phis and thetas, which are difficult to type into WebWork and whatnot, right? We don't have a phi or theta button, right? But it wants u's and v's to be our parameters, to be our variables. They say, okay, fine. Well, we can switch it out if you want us to. So I'm going to write 5 sine u cosine v. So you can see that basically I'm just, instead of phi, I'm going to be using u, and instead of theta, I'm going to be using v. Next up, my y coordinate, we're going to be doing 5 sine u sine v. And then finally, for my z coordinate, we're going to be doing 5 cosine u. So this right here would be a perfectly good parameterization. Whenever you write down a parameterization, you always want to include in the domain for your variables as well. This will come in a lot more useful later on when we're doing things about surface area or volumes or things like this. And so we want to hit kind of all of the points on the sphere once. And so we're just going to steal the same boundaries that we did from last section, right? Theta is going to be ranging from 0 to 2 pi. Phi is going to be ranging from 0 to pi. And so in this case, well, again, phi, we are using u for that. So I'm going to do u from 0 to pi. And theta, we were doing v. So we just swap those out, and now those are our correct bounds. We'll hit every point on the sphere and exactly once. And so now, as I promised, right, the original question that Lev proposed was, well, we wanted not 5 here, but we wanted just any old random radius, a capital R. But now that we've done this with something a little bit more concrete, right, we can see that this equation right here would just simplify down to rho equals capital R. And so instead of a 5 everywhere, we could sprinkle in capital R, capital R, capital R. Lots of capital R's everywhere. And so this is a way that I sometimes like to use because, I mean, sometimes when you get just so many variables and whatnot, it's a lot to juggle. And so sometimes, especially for the first problem through and whatnot, I like to do it for a specified value, and then we can talk about a more general case. But you can see, right, there's nothing kind of extreme here about just switching your 5s to your capital R's. All right, let me go ahead and pause and see what questions have come up. Let's see, where does the composition of this triangle come from? Is it always the same? Oh, so this triangle right here. Yes, and so this just comes from, really I should draw it in 3 space. So something like this. So here's my positive z-axis right here. So this, of course, is going to be some z height. Phi is supposed to be this angle that you move away from the positive z-axis. Rho is a 3-dimensional radius. So that's going to be this right here. And R is a 2-dimensional radius. telling you how much to come out of the z-axis, right? And that's just from cylindrical there. So yes, this is always the same triangle here. Good. Let's see, what else do I have? All right, silly question, thank you. What is your skincare routine? Not a whole lot. So are the parameters always independent of each other? Ideally. So the question is, are the parameters always independent of each other? Not 100%, right? If you get a complicated enough surface, the answer may be no. But I quite often find if you're doing things right, and especially at the level that's appropriate for timed assignments or web work homeworks and stuff like this, that yes, if you're doing things right, they should be independent from one another. I don't understand this question. What does rho represent? So rho represents the three-dimensional radius, right? Rho has the equation that rho squared is equal to, in fact, let me just write down rho is equal to the square root of x squared plus y squared plus z squared. This should look a lot like the distance formula back from 12.1, right? So the square root of, and I think we had x minus x naught squared plus y minus y naught squared plus z minus z naught squared. So this is a distance from the origin. So we're fixing a specific distance from the origin in 3 dimensions, x's, y's, and z's. I have a request to get the entire problem on the screen. That one's easy enough. So is 5 both r and phi? Interestingly enough, it's neither. So r is just rho in this case. Why is u from 0 to pi? Because this is all you need to get all of the points in the sphere once. So basically you're just looking, right? Rho is telling you where you should be looking up and down, right? So I think about, whenever I think about spherical coordinates, I always think about programming a turret or something like this, right? That's firing some projectile or whatnot. And so the things, right, if you were programming a turret, you're gonna need to tell it how hard to fire, that's your rho, essentially. Where you should be looking left and right, that's your theta. And then where you should be looking up and down, and that's your phi. And so when you're looking straight up, that's at phi equals 0. And when you're looking straight down, you're at phi equals pi. And then you can kind of rotate to hit any point. If you go beyond pi, then you're like shooting behind you or something like this. It's very awkward. Why did you assign pH to be X and TH to be Y? Random? Yeah, so I'm assuming that this is maybe about my choice for U and V here. And yes, it was random. You can switch that, and that's fine. Okay, with that, let's go ahead and proceed. This talks about if you were to go ahead and fix some things, right? And you can see that here we have some different parameters, theta and phi. Remember, I just brought it up, right? Because quite often our web work homeworks has these things in terms of U's and V's or sometimes S's and T's. And I just want to make sure that everyone gets right that there's not a whole lot in a name. You can go ahead and switch the name to U's and V's if you want. But this was, excuse me, the intended final answer. And if you restrict down and you think about only for a very specific theta or only a very specific phi, right, this will end up corresponding to the longitude or latitude. So again, kind of if I fixed a theta value where I'm looking left and right, then I'm going to get this very specific longitude. If I fix, however, a very specific phi where I'm looking up and down, right, this is going to give me a very specific latitude, right? And so, yeah, this is how you can kind of get these. And this is important because we're going to be using this idea right here for the last problem that I brought up about these normal vectors or tangent planes. We're going to use this in order to get some tangent vectors here. So by restricting down to just curves, we've already talked about in 13.2 how to get tangent vectors to a curve. So we're going to get some tangent vectors here. And with those tangent vectors, we're then going to take the cross product of those, to get a normal vector sticking out of this thing at nice 90-degree angles. And then from that normal vector, we can get a tangent plane. So that's why this is important, restricting down to specific values for theta and for phi. So this is a little bit of foreshadowing here. I don't want to get too much into this. I agree that it's complicated, but this is what we're going to be doing for our last problem of the day. All right, let's go ahead and parameterize this cylinder. We'll do this one fairly fast, and then we'll go ahead and talk about surfaces of revolution. So parameterizing the cylinder, again, the fact that it's cylinder, I'm going to borrow from cylindrical coordinates, right? And so when I naturally think about this, I'm going to be thinking about x is equal to r cosine theta, y is equal to r sine theta, and of course, z is just equal to z. This, of course, right, if I want it to satisfy x squared plus y squared equals 1, well, that's the same thing as r squared equals 1. Remember, that's just a transformation, an equation that we have from our cylindrical coordinates. And then if I take the square root on both sides, we have r is equal to 1. And remember, normally it would be plus or minus, but in this class, we're restricting to positive radiuses. So r will always be positive and rho will always be positive. There's ways that you can make this work if you allow for negative r's and negative rhos, but it's not necessary. And especially because we're just looking for a parameterization, right? We're going to go ahead and just stick with the positive one. And so if we go ahead and substitute these things in, right, I get 1 cosine theta, 1 sine theta, and z is just z. So if you'd like to, you can go ahead and parameterize this, where your parameters are theta and z. Or, right, maybe you want other specific parameters, right? Maybe you want something like s's and t's. So let me go ahead, right? X is cosine theta, y is sine theta, and z is just itself, right? Notice that this equation doesn't have any z's in it. It's kind of like the first cylinder that we did, right? Where we started with a parameterization, right? And we worked backwards and got a Cartesian equation. If you wanted to do s's and t's, and let me switch up, I'm going to do the ijk notation here instead of with the vectors. Let me go ahead and for theta, I'll use t. So I'll do cosine of t times the vector I, because it's in the first component. I'll do sine t times vector j, because it's in the second component. And then if t was theta, then s should be z. So I'll do s times the vector k. So these would be two perfectly good parameterizations. One's using thetas and z's, one's using s's and t's. Again, we should always specify, though, right, our range, our domain for our variables here. So theta, you would get all the points by going from 0 to 2 pi. And z would just range, excuse me, from negative infinity to infinity. There are no restrictions on z here. Or if you were to switch it up and do the s's and the t's, likewise, you could write it like this. T ranges from 0 to 2 pi, and s, which is taking the place of z, ranges from negative infinity to infinity. All right, with that, let me go ahead and see how the questions are going. Let's see, I have a few of those that took care of that. What is the difference between little r and capital R? So that's from kind of this last one. Capital R was a fixed radius. It was some number. You could have also used capital A or capital B or anything like this. Little r is the two-dimensional radius that your point is away from the origin. So for any given problem, u and v are just variables we use to replace other variables. Yeah, that's a fine way to think of it. Again, it's a transformation of variables here. Yes, that's all these parameterizations are. Yes, r is treated like a constant. All right, I think that we have this. This sphere cylinder. I guess maybe I should have skipped down. Why does r squared equal 1? So that's from our equation, right? We were given x squared plus y squared equals 1. So that was the surface we were told to parameterize. Why isn't z equals 1? Well, because we don't have any z's in this equation, right? So there's nothing that restricts z. This is going to be the cylinder, right? So it looks kind of like this. Notice that it's missing a variable, right? And it just goes on forever. So maybe at some points, z is equal to 1, right? So maybe at this point right here, z is equal to 1, but also z could be equal to 0, oops, equal to 0, or z could be equal to negative 500, or anything like this. This is not to scale now. All right. With this, I do need to continue kind of moving on. Again, if you have questions that aren't resolved, I'll be happy to talk to you about these after class, or on Piazza is fine as well. This one I'm going to skip for time. And in fact, in my pre-class video, I did one very, very similar to this. The only difference is mine had a 3 right here. So I invite you to watch my pre-class video on this subject, and you will see how to do this problem. And I'll talk you through it and all. All right, for surfaces of revolution. You got one of these on kind of this last homework WebWork 9, number 12. You got a problem like this. And so I wanted to spend a little bit of time on surfaces of revolution. And in particular, right, how do we rotate things around maybe the x-axis? So in this case, you can see that there are circles here. They're kind of independent of x to some extent, right? Once you kind of have fixed this down, right? But this is where the circles are. So you can think that all of the circular stuff is happening in the YZ plane, right? You kind of see this in the YZ plane, that circles are happening. In the X direction, right, you don't see, I mean, this is where all the different circles are going on, right? But if you were to just restrict down and think about maybe the XY plane, you see like a curve like this. And this is this curve, y equals f of x. So we want to take that curve and we want to spin it around, right, this x-axis, or that's going to be this YZ plane, right? And so this is the way that we can go ahead and do it. Again, you can see all of the circular stuff, the fact that we're taking this height and spinning it around in the XZ plane, right? Or around the x-axis. All of that circular stuff is happening in the y coordinates and the z coordinates. Of course, we need to specify where we are, what is our x value. And we also need the height, right? Remember, the height depends on x, y equals f of x. So once you tell me what x value we have as one of our parameters, the function will tell us what the height is. And remember, this height right here is acting as a radius, right? This is essentially a radius off the x-axis. And so we take this and we generate a circle. So this is why you can see kind of the height is the radius. That's the r cosine theta. Here's the r sine theta, right? So this is just the radius, the height, this y value, the f of x. That's your radius there. So that's why this works out so well. So now let's go ahead. Now that we have this information, let's use it for something, right? Let's see if we can apply this to this question right here. And again, this is very similar to a WebWork question. We want to parameterize the surface obtained by revolving this equation, y equals e to the x, about the x-axis. So if I was to go ahead and draw this, here's, I don't know if I really want it like this. Maybe I should have rotated this around a little bit, but I'll stick with it. X, Y, Z. I have to try to draw this thing in the XY plane, which is flat on the table. So it's a little bit weird. It's going to look like this. Here's e to the x, right? As the x's get larger in this direction, the y's get larger. I'm used to looking at it like this, right? But I had to put it flat on the table. So that's kind of why it ended up turning out like this. Okay, and we'd like to revolve this about the x-axis. So I want to go ahead and take this. And at each one of these points, I'm going to go ahead and spin it around the x-axis. And so you get kind of this interesting horn sort of shape, or this black hole sort of shape. And right now we just want to parameterize this. Later on, we may want to ask what's the surface area for a piece of this, or how much water could it hold, right? What's the volume of it? Things like this. And from this equation up here, we have that we can parameterize it. Excuse me. Our first value is always going to be just x. Our second one is going to be f of x. So in this case, our f of x is e to the x times cosine of theta. And then we have e to the x times sine theta. Here, there are no restrictions on x. However, you get all of your theta information, right? You don't need to allow this to go on forever. And of course, computer programs and software and stuff like this would prefer if you didn't let it go on forever. And so you get the entire picture after 0 to 2 pi. So this is kind of the minimum values that you need in order to sketch the entire thing. All right, so this is the good parameterization for this. Let's see, this was just a minute ago. Does this format of sine and cosine hold true for all examples? No, not necessarily. And you have to be a little bit clever about this, right? Here I came up with how to rotate about the x-axis. So a natural expansion to this, and I see that I'm already a minute over, right, is how do you rotate about the y-axis? So I invite you to think about how would you set this up if you wanted to revolve around the y-axis rather than the x-axis. All right, well, there was a couple examples here, and then I also have the example that I created. So I'm gonna skip that other stuff for a minute here. I see that it's 2:40, so class is formally over. If you have to leave, I certainly understand. I was a student once, and I know you have other places to be, and 50 minutes is a long time for this. If you can stay, great, and I'll continue to answer your questions, all that sort of stuff. But I'm gonna do this problem, and I'm gonna record it here. And I'm going to post it with the other lessons. So if you want to hear this live, if you want to ask questions about this, please stick around and I'll take your questions about this. So I'd like to find an equation for the tangent plane to this surface. So this is very interesting surface, and I thought, well, it'd be a good idea maybe the first time through this to go ahead and see what the surface actually looks like, right? Because this is kind of quite mysterious. And so I went ahead and I graphed this surface, again, just in this Monroe 3D Calc plotter. If you would like to actually play with this, right, I have the link right here. And bit.ly links, I believe, are case sensitive. So make sure to copy down the uppercase and lowercase and all that sort of stuff. But you can spin it around and all that sort of stuff. And again, our goal is to come up with the equation of the tangent plane. We want a plane that just barely touches at this point. And what should the equation for this thing be? And of course, right, anytime you want to know an equation for a plane, you always need two things. You need to have a normal vector and you need to have a point that it intersects, right? Because planes look like this. They look like A times X minus some X value, B times Y minus some Y value, C times Z minus some Z value. You add them all up, set it equal to 0, right? This was this whole original dot product equation just from back in 12.5, right? This is the expanded form of that. So already we know something, right? We're interested in the tangent plane at a very specific point, at the point 5, 2, 3. So we have that special X, Y, and Z value. So already I could plug in this. And if this was a free response style question on a quiz or in an exam, right? You should certainly do this at very least, even if you don't know how to do the rest, right? Because you can get partial credit, right? So at very least, you do this. Now, next up, I talked about before how we can come up with tangent vectors. We're going to need a couple of tangent vectors to this thing. So if we have a couple of tangent vectors, thinking about maybe here's some curve here, we can get maybe the tangent vector at this point through this curve. And then here's maybe another curve. And again, I'm just kind of stealing curves that are already on here. And we could come at this point and take a tangent vector in this direction. Well, if you take the cross product of those tangent vectors, you're going to get a normal vector. And that's going to be the last missing piece that we need in order to solve this, right? We need a normal vector. A normal vector tells us our A, B, C. Those are just the coordinates for our normal vector. And so again, our goal is this. Get a couple of tangent vectors, right? Corresponding to some curves here, then take the cross product. That's what we're going to be doing. So, okay. The first thing that we need to do is, right, we have this wonderful equation here that spits out X's, Y's, and Z's, right? But the input is U's and V's. So it'd be very useful, right? We already know that our special point related with X is 5, our special point related with Y is 2, and our special point related with Z is 3. Those are just given to us. But these should somehow correspond to special points that we could plug into this thing, right? There should be some U and V that helps us, right? Because this is the thing that we have to play with. We have to plug in things to it, right? And hopefully get some of these curves and then maybe take derivatives to get direction vectors, all that sort of stuff. And so we need to stare at this for a minute and we need to try to figure out, well, okay, this needs to output 5, this needs to output 2, and this needs to output 3. What should the inputs be that would give us those special outputs? And I'll pause for a second here and see if you can tell me what would those inputs be. So a couple people have answered already. I see 2s and 1s. U is 2 and V is 1. So I agree with this, but when you first set this up, right, the way that you would go about this, doing some algebra, is that you would set your first coordinate, U plus 1, equal to 5. And so the first time through when you solve this, you get U squared is equal to 4. So U could be either plus or minus 2. So somehow you had to decide that 2 was the right answer and not negative 2. Well, notice when you go and you do the same sort of work for your Y coordinate, you get V cubed plus 1 is equal to 2. You get V cubed is equal to 1. And remember, square roots have this problem with the plus and minus. Cube roots don't. When you take the cube root of 1, it's just 1. So that we get that one definitively. And then finally, the last coordinate here actually helps us definitively say that U needs to be 2, right? Because when we add these things together, we need to get 3, right? And the only way that works is if U is equal to positive 2 and V is equal to 1. So that's how you would get that correct Z value. All right, so now we have some specific points that we're interested in terms of U's and V's. So in order to get these curves here, just like when we were talking before with the sphere, we're going to go ahead and restrict down to a specific value, right, for one of these parameters, for one of these variables. So I'm going to go ahead and think about, for the time being, our surface, but restrict it down to U equals 2. V can still be whatever it wants, but U is going to be equal to 2. And what this is going to give me is just an equation in terms of one variable. Let's go ahead and see that this works. So I'm going to go ahead and write this in the vector form up here. So if I plug in U equals 2, I'm going to get 2 squared plus 1 is 5 for my first coordinate. For my second coordinate, I get V cubed plus 1. And for my third coordinate, I get U plus V, so 2 plus V. So as you can see now, that this is just a curve, right? This is just, it only depends on one variable now. It only depends on V. And so this is going to be the one where X is being held constant. It would look like this one right here, this red line. This is R of V, what we've just found when we plugged in 2 for U. So at U equals 2. So we want to find its tangent vector. So I'm going to go ahead and take a derivative of this. So let me stay consistent with my coloring here. So I'm going to take a derivative of this. We get 0, 3v squared, and 1. And this would give us our tangent vectors all along this curve, right? So all along this curve, we get a whole bunch of different tangent vectors, all tangent. But we only want the tangent vector at a very specific point, right? When v is equal to 1. So we don't really care about those other ones right now. We want when v is equal to 1. This is going to be our special tangent vector that we're interested in. Oops, I did a bad job multiplying by 3 there. So this is one tangent vector. Again, remember, we need a second tangent vector, and then we need to take a cross product. So let's do similar sort of work here, maybe a little bit faster now. This is where I'm going to let u stay as a variable, and I'm going to restrict down v. So again, v, our restriction down to v was supposed to be v equals 1. Again, that's just the special v value that we know is going to end up hitting this point. This is going to be mapping this green curve right here, essentially. So if I restrict down again to from my original equation here, and I just plug in v equals 1. So everywhere I see a v, I'm plugging in 1. Well, the u stuff doesn't change so much. This one does. And v equals 1. So this is going to be u plus 1. Again, we take a derivative. And again, we plug in our specific point, right? We want to know the tangent vector when u is equal to 2. Now we have our two directional vectors, our tangent vectors. We can take the cross product of them, 0, 3, 1, 4, 0, 1. When we take the cross product, we always get stuff with i's, minus stuff with j's, plus stuff with k's. Crossing off the first row and the first column, we get 3 minus 0. The first row and the second column, we get 0 minus 4. And the first row and the third column, we get 0 minus 12. 3, positive 4, negative 12. This right here is our tangent vector. This one right here. 3, 4, negative 12. This is the last bit that we need for a tangent plane. So we take this, 3, 4, negative 12. We plug it into our equation. And now finally, we have solved it. This right here will be my final answer. And you'll see a few questions like this in WebWork. Some of them have you solve z equals, right? That's perfectly fine. We could rearrange this and solve z equals. But yeah, this is the big thing here. So this is how you can come up with an equation of a tangent plane. Okay, let's go ahead and I'll do some Q&A here. And then I'll hit stop the recording and just see if there are any other questions. I'm going to start at the bottom and kind of work my way up. How do you do the parameterization of the boundary curve? Well, this you just need to know what the boundary is. So this one doesn't really have a boundary. It goes on forever. But you're going to just go ahead and plug in one of the boundary values. So if there was a boundary, for instance, at, I don't know, u equals 5, right? You can just plug in u equals 5 into it, and that restriction will give you the boundary curve. How do you know which tangent vector goes first in the cross product? It doesn't matter. Essentially, this is multiplying by -1. And of course, when you multiply by -1, right, you're just going to get -3, -4, positive 12, and this is still -0. And that would also be the same plane, the exact same plane. When you go ahead and you solve for z and everything, you can see that you get the exact same plane. So yeah, that's the nice thing, is that it doesn't matter which one you put first in your cross product. It's a fun question, though. How do you know that the R of V corresponds to red? I mean, this was just, yeah, I did a little bit of looking at it in my head. It doesn't super matter which one corresponds to what. What I was actually looking at here is that I saw that when I made this restriction down, let's see here, when I plugged in 2 for u, and so now my only parameter was v in this case, I saw that the x was constant. So that the x is constant. And so then I went back up here and I looked at, well, which one of these is the x is constant? Well, I can see here's y and here's z. X is this one right here. And so if x is constant, right, it's probably like 1 or 2 or something like this, right? This is kind of this red line here. Now all of a sudden I'm a little bit worried about this. Yeah, I think x should be, but that doesn't look particularly constant either. Maybe it's that these lines right here don't actually correspond. This is maybe something that the graphing is doing that sadly doesn't exactly correspond to the u values and v values. I was hoping that they did, but I'm less confident now. Good, thank you for pointing that out. Why not make v equal to 1? I was dreaming that I did at various points set v is equal to 1. Yes, so all throughout here, I set v is equal to 1. If you set both u equal to 2 and v equal to 1 at the exact same time, then sadly, you're not going to get a curve, right? You just get that specific point. You're going to get this point again, 5, 2, 3, and that's a perfectly fine and happy point, right? But it just doesn't happen. It just doesn't help us get directional vectors. So that's the problem with just doing that full restriction, is that you're not going to get tangent vectors from that. Let's see here. Would either normal vector work? Yes. And any scalar of it would work. It would all give the exact same plane. Are there curves for the exams? No, not, well, it's been a long time since we've ever had a curve for a particular assignment. We look at the distribution of grades at the end of the semester, because, right, admittedly, right, the quizzes and the exams, if you were to look at all of the assignments or all the grade items, right, they do have a lower average than, for instance, attendance, participation, homework, things like this. And so, yeah, those are always a little bit lower, but also there's a little bit of kind of normalizing that happens naturally throughout the semester, right? If we end up writing a hard exam 1, then it's very possible that exam 2 is easier, right? Kind of the exam writers look at this and say, oh, wow, that was harder than we were expecting. Let's back off a little bit. And likewise, if the exam average is very high, they look at this and they could say, oh, well, the exam average is very high. They can handle more. Let's include some maybe more interesting questions on the next exam. So no, there's not curves for particular assignments, though. We look at it at the end. Why do you want to take the cross product between RV and RU? Well, we don't really want, not between the curves themselves, but the tangent vectors. So the tangent vectors here are what we are taking the cross product with. And that's in order to get this normal vector here. So my goal was trying to find this normal vector because a plane requires it. A plane always needs a point and a normal vector. And so somehow I needed to get that normal vector. And by taking the cross product of the tangent vectors, that's how you do it. How do you solve for A, B, and C again? A, B, and C in this are just quite literally the components of your normal vector. So once I took the cross product, right, I found that the cross product was the vector 3, 4, negative 12. That was this work down here. And so the first component 3, the second component 4, the third component negative 12. Excuse me. All right, I'm going to stop recording